Good day to everyone. A warm welcome to our analytical technology assignment. Well, the chosen topic for this assignment is that of the calibration methods, which is the first unit of the syllabus. We're going to take you through the different types of calibration methods and which ones scientists use depending on the type of problem that they're facing.
Hello, in this video we're going to talk about calibration methods that are used when people use instruments to make chemical analyses. We're going to talk about the external standards, the internal standards, and the standard addition methods of calibration. Instrumental methods of analysis require calibration, and they have signals that usually can't simply be related to the analyte concentration or the analyte amount by an equation. So the signals are often something electrical, like the voltage or current from a detector's circuit. The signal, the information that you're using, could be the height or the area of a peak in a chromatogram or a spectrum. The signal from the analyte in the unknown must be compared to signal from the analyte in standards. That's where it's different from the classical analyses. The comparison that you have to make is mathematical in nature, and so the signal ideally will have, be able to have an equation between the signal and the concentration of the analyte, but that equation has to be determined using standards. Okay, so if you do not expect sample-to-sample variability, and nor do you expect interference effects to be happening, well, then you can just use the external standards method of calibration, which is the most basic, the first calibration method that people learn about usually. So let's say if you did expect sample-to-sample variability, but not interference effects, well, then you would use the internal standards method of calibration. If you did not expect sample-to-sample variability, but you did expect interference effects, well, then you would use the standard addition method. So let's talk about the most basic one first, the external standards method of calibration. One that you already know. Most people learn about this one first. So you have your unknown, say it's an analyte in solution at some unknown concentration, which we'll mark with X. Well, then for the analysis, for the purposes of the analysis, you would make up a stock solution of the analyte at some known concentration that you would make up as accurately and precisely as possible. Then you have a set of flasks. Into one flask you would put only the unknown, and into the other flasks you would put variable amounts of that stock solution. So this is a basic point you already know, but it's a real important point. The unknown goes into one flask only. The stock solution of the analyte then goes into the other flasks. They're not mixed, they're kept separate. Fill them to the total volume, analyze. Let's take a look at some data, some example data. Say we've got a set of standards which includes a blank, varying amounts of analyte in there. This one actually had no analyte, but then we recorded signals, probably absorbance measurements. Maybe you can imagine that this would actually be an absorbance value, but basically absorbance, that signal, would be directly proportional to the analyte concentration. Well, then, don't forget that we made up a little solution of the unknown. We measure its absorbance. Don't forget that we're out to figure out that concentration of the unknown, so we measure its absorbance and then just rearrange this equation and plug that absorbance of the unknown into there and just solve for that unknown concentration. Looks a lot like the external standards solution of calibration until you bring in this stock solution of the internal standard at some known concentration. Okay, so then you have the same set of flasks. Add some of the unknown to one flask, add the stock solution of the analyte in varying volumes to the other flasks. Well, this still, up until this point, looks a lot like the external standard method. Until now, when you add a constant amount of the internal standard to each flask, fill all the flasks to the volume and analyze it. Okay, so here's some example data that's generated at Georgia Southern University. When students do an analysis of gasoline for the analyte toluene, which is universally present in basically all brands of gasoline in pretty large amounts, say around 10% or so. So we're analyzing for toluene but it's a chromatographic method, gas chromatographic method, with this manual injection, which is a pretty large source of sample-to-sample variability. We have an internal standard, chlorobenzene, which it had a little higher boiling point, comes out a little bit later, quite a bit later, certainly can keep it separate from the toluene, yet signals for both in terms of we use the areas of those peaks. So when you use the internal standard approach, actually you plot on the calibration curve on the vertical axis the ratio of those signals. So you would, for each solution which gave a chromatogram, you would take those two peaks and you would plot the ratio of the area of the toluene peak divided by the area of the chlorobenzene peak. And then you would plot that as a function of the concentration of the toluene. Here we use volume percent. Okay, what do you do with that data? Well, that calibration curve is a line again, but plotted on the vertical axis is the ratio. So it just looks different right here because you're plotting the ratio. It's always the ratio of the analyte divided by the signal from you analyze the unknown that you make up, you get your ratio from the unknown, you plug that into this equation, and then you solve for the concentration of the analyte in your unknown. Straightforward enough method. So here's how it looks. Okay, you've got your solution of the analyte and your solution of the standard. Analyte, that's a known concentration. Now you don't have an internal standard here, but you make up the solutions a little bit differently. Let's show you how. Okay, you add a constant volume of the unknown to each flask, not just one, but all of them. Constant volume. Say if these are like 10 mil flasks or something like that. Say for example it'd be 1 mil, 1 mil, 1 mil, 1 mil. Constant amount to all of these. But you add variable volumes of that stock solution to all flasks but one. Say if these were, say this is like 2, 3, 5 mil or something like that. Variable. But into one 0 mil of this. You just don't add it to. So this is what the data might look like. And something you could do is determine the equation of that line by linear regression, least squares analysis. And then so you'll see, taking the ratio of the intercept divided over the slope would cause some nice mathematical things to happen. Certain factors would cancel out because they appear on both the top and the bottom. And so on the right hand side of this equation, you boil it down. There's only 4 variables, 4 parameters. 3 of those are constants, and 1 is the concentration that you want to solve for. So you would just, after that simplification, rearrange and just solve for that unknown